shows you the inputs and outputs of every layer. It's quite long, but imagine how long VGG19 would be. Okay, so this is where I should just put some notes in for you guys. Training our little VGG model. Alright, so we have our callbacks here. Same typical callbacks we've used before. Checkpointing, early stopping, and learning rate adjustments on plateau. And a number of samples that we've gotten from the generators before calculated. And we're going to train for at least 10 epochs. You can train for more. Always recommend train for more, but if time is of the essence, and this is more for practical educational exercise as opposed to us trying to get the best performance out of these models. So what we're doing here, we're just testing our little VGG model. It's this one here, just to see how it performs on our dataset. So I've ran this for 10 epochs, as I said, and let's see how the first epoch performs. 15% on validation accuracy, not great, okay? And again, not great on the training accuracy too. But as we train, steadily improves. Look at this column here on the training accuracy. Keeps going up and up. And also, let's look at the validation accuracy. It also keeps going up and up. So I'm pretty sure if I left this to train, maybe for like 50 epochs, I could have gotten 90s in the percent in accuracy. So this is good to know. So we do see the flexibility and power of a simple VGG model that honestly doesn't take that long to train. 500 and something seconds. So that's not too bad per epoch. Alright. So this is how, let's look at the performance of this model. So let me just title this section for you guys to make this notebook a bit cleaner. Okay. Oh, my C key is giving some issues, it's sticking about a bit. So look at our confusion matrix here. So we can see a high number in the middle rows, in the diagonal row here, which is also good, always good. But we do see some issues here with some characters being basically misclassified. So we know this is a 77% accurate model. So we know it is going to have some issues, but it's generally going to be quite good. So we can see which characters it's performing poorly on. And let's look at the F1 score to find that. Mayor Quimby, interesting. Alright, it's a poor F1 score for him, but a super high precision rate, so that means there's a lot of false positives. Alright, and no one else seems to be nearly that bad. You can definitely see Mayor Quimby here being misclassified as Mo. That is interesting. Alright, but generally we see a nice smooth diagonal throughout here. This is a much easier way to visualize this data, okay? So I'm going to load our model that I saved from before. Takes about 10 seconds. I hate loading models for this reason. There we go. So this is some messy OpenCV code I've created. However, you can spend some time going through it. It's not super difficult to understand. We've used similar code before, but basically we're just going to display. Right, good. Display our predicted over our true. So let's see how it performs. Good, this is Millhouse. This is not Homo. This text is too big, I can resize it after. Actually, let me show you how to resize it as we're here. So as you see, this function here, draw test, is where we're actually drawing our text. So this is the font size. So we can reduce the font size here, and we see how it becomes. So good. If you're wondering though, what this other two here, this is the thickness or the boldness of the font. And there are a number of fonts we can use in OpenCV. This is one of the nicer looking ones in my opinion. So let's take a look at our classifier results. This is Charles Montgomery Burns, and it is in fact Charles Montgomery Burns. Pooh, very good. Krusty the Clown should be easy to spot given his green hair. Very good. Sideshow Bob, pretty good. Krusty again. Mo. This is clearly not Principal Skinner. This is Lisa. However, because she's wearing a cap, that's probably why it got confused. Although the cap is not similar to what Principal Skinner would wear, so I'm not sure why our classifier is doing that. This would be a good time to actually visualize how our classifiers perceive the characters. Apu again. Edna. Abraham or Grandpa. So that's pretty good. So for a classifier that's 77% accurate, it actually performed fairly well on our test data. Okay, so I hope you had some fun playing with little VGG. It's a very good model in my opinion, and you can use and adapt this to a number of your applications if you want. Okay, thank you. Okay, hi and welcome to chapter 17, where I talk about advanced activation functions and initializations. Those are some other features that Keras allows us to configure when tuning or creating our CNNs. So before I begin, I'm going to talk about the dying ReLU problem and introduce you to why we need leaky ReLU, ELU, and preLUs as well. And then I talk about advanced initializations. Okay, so let's get started. Hi, and welcome to chapter 17.1, where I introduce to you some advanced activation functions. So, if you remember from our earlier slides, activation functions are what introduces the non-linearity that provide neural nets with their incredible performance. However, I always said before, ReLU is basically the activation unit of choice for our CNNs, and I basically left you at that, and you probably will always use ReLU from now on. However, ReLU isn't perfect, and I'll tell you why. There's a problem, and it's called the dying ReLU problem. So, when training, a number of ReLU units can often die during training. And what does that mean? This happens when a large gradient flows through that neuron, which causes the weights to update in such a way that the unit never activates anymore. So regardless of future input data, that ReLU unit basically is always going to be switched off. So you're going to have a part of the network that's effectively dead. So what happens is that exactly as this says here, the output of this unit is always going to be 0. So now we have basically a wasted unit and a wasted amount of connections in our network. And apparently sometimes as much as 40% of a network can be dead because of these dying ReLU units. So how do we fix the dying ReLU problem? Okay, so firstly, let's take a look at the different types of ReLU functions I'm about to discuss. You know ReLU is a standard clamping, basically, at 0 activation function, right? Everything over 0 is allowed to pass. Everything negative is basically clamped at 0. However, what does leaky ReLU do? It has a small negative slope, that's a green one here, and basically it's just like a linear function. However, there's a parameter in front of it that basically allows it to not grow that much. So it's basically a factor that basically limits how big, how negative it can go. What about preLU? Now preLU stands for parametric ReLU, and basically it is very similar to leaky ReLU. However, parametric preLU or parametric ReLU basically has another function, another parameter that can control the steepness of the slope. And ELU, which is exponential ReLU, basically the negative portion of it follows an exponential curve with these parameters here. Okay? So ELU tends to be a good mix of the good parts of ReLU and leaky ReLU. However, it can saturate on large negative values, as you can see here. Okay? So there are some other exotic, and I call them exotic because they're not commonly used, some activation functions. There's creLU, which combines or concatenates the outputs of two ReLU functions, one positive and one negative, thus doubling the output value. Not entirely sure when you would use this, but there's a decent paper here, you can read about it. There's also ReLU 6. So basically ReLU 6 is just capped at -6. There was no special reason for selecting 6, other than it worked best for the SFR dataset according to this paper here. And there are many others as well. There's max out, offset ReLU, you get the idea. However, in practice, I would suggest you use leaky ReLU or ReLU. So when do you use something other than ReLU? So we've just seen some of the variations here, but there's no hard and fast rule in deep learning. That's why some people call deep learning more for art than a science. That's kind of true because of the number of factors, and basically there's so many interchangeable dependencies. How does your data look? What is it going to be used on? There's a lot of things to configure in the network. That's why a lot of people say it's an art. However, there are some general rules you can use that will generally get you good results. Okay? So, generally, a good rule of thumb is to always use ReLU first, and then you adjust learning rates to get the best accuracy you can with your CNN at first. Okay? Once that's done, then you can start experimenting with different ReLU functions. You can go from leaky ReLU to ELU as well. That's a nice progressive step you can take. However, in most cases, you can just skip leaky ReLU and go straight to ELU. I always find I get better results with ELU compared to ReLU. So if you want to just try to get the best network and best accuracy as possible, use ELU, okay? Okay, so this brings us to section 17.2, where we talk about advanced initializations. So something we sort of glossed over in this course is that we always say our starting weights are random, our initial starting weights, but are they truly random? And that means, are they pulled from a uniform distribution? Well, kind of yes, that is the Keras default. However, there are a number of other initializations that Keras offers. So let's take a look. These are the many initialization functions Keras can provide us with, and let's take a look at how they look. All right, so this is what a uniform distributions one would look like: random normal uniform, some glorot normal, orthogonal, identity, glorot uniform. So you can see that there are some definite differences in these functions. You can do a normal distribution style where it's more the bulk of the initializations will be centered around 0. Or you can do some where it's just randomly between 2, like 0.1 or 0.01, that sort of thing, okay? So we have tons of initializers. Which one do we use? So generally, we always want to use a 0-centered initialization within a small range. Example, -1 to 1 is typically best, and this was recommended in Stanford's CS 231 course, computer vision course, which is a course I highly recommend you take. It's pretty theoretical, but it goes into a lot of detail, especially in the training part of CNNs and neural networks as well. So some other good choices for initializers: HE normal, it works pretty well when you're using ReLU activations. Glorot normal works pretty well too. And glorot uniform, which is the Keras' default random initializer. If you're going back, that is what it is here. So most times, just so you know, the initializer of choice you choose, it doesn't really impact your accuracy that you get in the end. However, it can definitely impact the number of epochs we take to get there. So it is something you can experiment with, maybe after the fact, if you think, for some reason, like you read in a research paper, that if you're using maybe an inception style model or a ResNet 50 model, it works better with this type of initialization, then you change it. Otherwise, I would just stick with the Keras default. Okay, so welcome to chapter 18. This chapter is titled Deep Surveillance because I'm no longer teaching you new theory here per se. What I'm going to do now is going to be like a case study practice project where we build basically an emotion, age, and gender recognition using face detection at first to find faces in an image or a video, and then we pick out what emotion is on the face or being shown by the face, the estimated age or predicted age of the person, and the predicted gender. So let's take a look at this section and see how I've split it up. So firstly, we're going to build a simple emotion or facial expression detector. And secondly, we're going to build an age and gender detector. And then in the last chapter, we're going to combine them both, and it's going to be called our deep surveillance monitor. So stay tuned, it's going to be a very cool project. Hi, and welcome to chapter 18.2, where we get to build our super cool emotion detector. So let's move on into our virtual machine and go to our IPython notebook, and let's see how it's done. Okay, so now we're here in our IPython browser, and let's go to chapter 18, deep surveillance, and 18.2, which is building an emotion detector with little VG. So let's open him up. And there we go. Should be loaded. Here we go. All right. So now, the first thing we're going to do before I even go into this notebook is let's go back to our file explorer here. And you see these three directories here. Let me explain to you, and a picture of me for testing. Let me explain to you what these three directories are. First of all, this age and gender one. This is our age and gender, which is in the next chapter. We're not going to touch this just yet, so let's leave this alone here. Now, this here, this for 2013, that's our data set that we're going to train it on. So let's take a look at this data set. So we have two directories. some other CSV files that we aren't going to use. We're just going to look at these here, how it's set up. So there's a train and validation as usual, and now we see these are the emotions here. Now, there is something I'm going to do, which I haven't told you guys yet, is that we're going to basically delete or discard the discuss directory, because I'm going to show you the plots afterward, but discuss only has 435 images. Alright, now let's take a look at fair. Fair has a lot more images, 4,000. So you can already see an angry, happy, neutral. Let's take a look at happy. How many faces are in this directory? Alright, it is 7,000. So it's quite a lot. So these are sorry, let's go back to this. This is a very imbalanced data set here. So there's two things we can do. One, we can move the discussed folder, the images here, into fair, because they honestly are a bit similar. It's a bit hard even for me to pick out what is fair and what is discussed. But for now, let's just delete it. So we press delete here, and let's go back to validation, and we press delete here. Okay, so now we're just left with 6 classes instead of 7, and 6 much more evenly balanced classes. So even surprise, I think surprise is the second lowest one. Yeah, it has 400 something images, but surprise, it's fine because surprise does look a lot different through discussed. So let's go back to here, and hard cascades, which I mentioned before. No, I haven't mentioned that yet. That's coming up in our object detection chapter. But hard cascades are basically a face detection. Well, it's a type of object detector, and we're actually not going to use eye detector, so we can delete that. Actually, just leave it in for now. We're going to use these here for basically our face detection unit. So let's go back to this notebook here. Alright, so this is how we load the data set. This is basically number of classes. It was 7, now it's 6. Now we're actually going to have the number of rows as 48 here to image size. And they're all grayscale. I don't know if I mentioned that to you. May have mentioned it in the previous section, I hope. But it is all grayscale images. Let's just take a look and see to verify that. Yeah, they are. So now we also are going to do some data augmentation, as has become routine right now. These are the parameters I've used here. Feel free to play with this as well. It doesn't make a huge difference sometimes, but you never know. Try it. Normal rescaling, normalization. Now we just put our data here. Notice we have a new parameter called color mode in both that I don't believe we used before because it defaults to color. Now we're specifying its grayscale, so just take note of that. So when you want to do a grayscale basically operation or training, you have to specify it here in your data gen flow from directory function. So now let's load this, and it's going to tell us how many images and how many classes. 6 and 6. Excellent. Alright, so now we move on to, let me just make this notebook a little more clear. Gonna put it here. This is basically our imports, well, basically our keras imports, and let's put another little thing here, so we can say this is our keras little VGG model. Okay. So now, as you've seen in the previous chapter with Simpsons, this is the exact same model we're going to use. So let's just run this, and here we go. Number of parameters. This does look a little different. I'm not sure. Oh no, because it's black and white, it's grayscale images. That is why the number of parameters are less. I am silly. Okay, happens a lot. It's fine. Now let us just label this as well. Training our model. There we go. So now we have basically some callbacks set here. I'm just going to pause this here because I realize I made some changes to this code. Actually, no, it's fine. I'm stupid. It is fine. So let's continue. Number of training samples. Let's just double check this because I'm not entirely sure if this reflects the classes we deleted. So 28273. Let's scroll up and let's see if it does. 28273. Yeah, it did. Okay, good. I'm doing things right for a change. Okay, good. And now, standard procedure with how we fit using our data generators. And our callbacks defined here, and model compile. So I'm not actually going to run this. I'm just going to show you what I've run prior to this chapter. And this was with 6 classes. All right, and now all the way down, you see we have 47% accuracy. Now that is not that good. All right, for 10 epochs, it's actually not bad. I've seen people use similar models, and actually sometimes much more complicated models. Someone used a full VGG19 on this, and it is very difficult to get past 70% accuracy. I am 100% sure if I train this for maybe 30 epochs, I'll get probably about 60% accuracy. So you can give it a try, alright? I'll probably do it and update it at a later date with this new model for you guys. So that's fine. So now let's look at the confusion matrix from these results here. There's 47%. Okay, so normally, what do you think of this? How would you analyze this? Now, I would say it's not that good, especially not that good at picking up fair. It rarely got much fair correct, all right? Now, what does it say about happy though? Now, these are counts, by the way, but even still, it's definitely good at getting happy, all right? But the others aren't that great. The others, you do see some mismatches here. You do see fairs not being picked up that well. I mean, it is being picked up. There's a different color difference definitely from here to here. We need a good monitor to probably tell, but there is a difference. But generally, you can tell here, fair is actually being confused with neutral and angry a lot as well. So this analysis says our model is decent but not great, which is obvious given its 47% accuracy here. And you can look at the F1 scores here. Definitely you can see exactly as I said, happy it's good at finding happy. It's hard at finding fair. Decent at everything else except neutral, although in my experience, at least for my face, it picked up neutral fairly well. Alright, so let's just load. I believe this was saved as, let me just make sure. It would be tree. Great. Okay, so now let's load our model. As usual, this takes about 10 annoyingly long seconds. Okay, quicker this time, oddly. Alright, so let's get our class labels again, because I believe they ran it before when it was 7 classes here. And now let's load some images. I'm not sure what's in this directory. Okay, so let's see how it worked. We predicted angry, and the true class was fair. So, okay, reasonable. Fair and fair, bingo, got it spot on. Fair, and it was neutral. Now, I wouldn't say this is a neutral expression. I don't know who labeled this, the data set. But, I mean, it's probably not fair either. It's probably some weird expression she's making. Okay, we predicted angry, and it's neutral. Now, I would say, yeah, probably neutral, but he does look a bit angry, doesn't he? Okay, so this one picked up, we detected fair, but it was actually angry. Close. This one, we predicted angry, but actually was fair. We predicted angry again. Predicted fair, neutral, it's true. Okay, so now we saw it there. So now let's actually try it on a picture of me, okay? So one thing I should have mentioned before, actually it wasn't in this code, it was in this code. This is how we use our HAR cascade classifiers. So now we're using something different. This is an OpenCV function. So we pointed the classifier we want to use. That was, let's go back to this one, all right? We have I, full body, and car classifiers, which I'm probably, let me just use space. Okay, they're tiny. I was going to delete them if they were taking up a lot of space, but they don't. Okay, so this is our face detector module. Now, what this module does, you can see we've created this object called face classifier. Now, when we get an image here, this is an image from my webcam. This is the function here that we're looking at, by the way. Okay, so we get this function, we convert it into a grayscale image, and then we pass this grayscale image of the webcam input into this. This is what does the face detection. This detect multi-scale function. These are some parameters to tweak the sensitivity as well, and how many times, like if you want to find small faces or large faces, you tweak some of the scaling parameters. So what it returns though is basically an array of faces. So basically, if there are no faces detected, it just returns some blank data because I'm using it in this function for some other stuff. But if it finds faces, basically it returns this. These are basically the location of the face. The X, Y, which is the top left. Basically, let's assume this is a box. All right. So X, Y is going to be, say, let's say this box I'm drawing right here, hope you can make it out, is the face. So the XY starts here on the top left corner of the face, and the width and the height is, width is this way, and height is like the down measurement, technically height still, of the face. So that's how we use now this OpenCV function here to draw a rectangle around the face, and then we take this grayscale image here, and basically we just crop it to get this face out of it. And what I do is just I run this for all the faces in this file, resize it correctly to what the classifier has been trained on to detect, 48 by 48, and I return an array of all the faces, all the rectangle dimensions, and the original image. I'm not sure why, but I was maybe doing something with it afterward. And yes, I think I was just putting the label on it afterward. So there we go. So we load my image. Let's run this cool function and hope it works after that explanation. Yes, okay, so thanks, I'm happy. I was happy actually. This was on my birthday 2 months ago. I was in Madeira, Portugal, which is a wonderful, wonderful island that you really should visit. I'm not getting paid to say that, just highly recommend it. My wife and I went whale watching that day. So yeah, so I was happy. So pretty decent. So you can load your images here. One thing to note, you can probably reduce the size of this text or start it maybe at the left corner here. So in case the face is more on the right hand side of the image, the text is not going to go outside of the image. So that's one thing you can do for your homework lesson. So now let's try this on our webcam, okay? So let's try this now. Okay, so you may have noticed a slight break in the code, and that was because when I ran this, I realized my t-shirt had a stain, which did not look good on camera. So again, I'm not dressed up, I'm just here at home alone recording this. So let me just run this, and here we go. So we see my face being detected for my emotion, or my facial emotion expression. My microphone right here, hope that didn't make any noise. So okay, cool. So right now I'm alternating between happy and neutral quite a bit. Surprise, hey, cool. I worked. Alright, nice. So it is working fairly well. So you can experiment with this, train it. One thing you should know, you see this bounding box here? This is actually bad, because just take a quick look at our data set here. Something you can do for a homework lesson, which I neglected to do for you guys, but these faces are tightly cropped. If you take a look at them, let's just open this quickly. They are, what I mean tightly cropped is they don't have that much space on the side. So generally, because I've just noticed this, this is not that tightly cropped here on the webcam. So let me just go back to this code. So if you wanted to change that, you actually can. This is actually, I actually did the opposite of cropping here. So I can actually change this to 2020, which was because the default settings for the face detector with hard cascades are quite tight. I actually previously added some spacing, some left, right, up, down spacing. So let's run this now, see what happens. Okay, so as you can see, it is a bit better. Maybe we can reduce the widths even more. Actually, we can eliminate the width altogether. Let's just W equal, okay, this is stupid. Just instead of W equal W, just not do that. And let's leave the height spacing at least. Okay, so I would say this is probably better. It's more tightly cropped around my face. And if we wanted to go even further, let's just not do any height adjustment here. And let's see what that gives us now. Okay. Yeah. It is definitely more stable and better, I would say. Okay, cool. So this works fairly well. Okay, I'm happy with this. I hope you're happy with this. This is a 47% accurate model, and it's doing quite well. Well, decently well at least. So what you can do as a homework lesson for you guys is train this for more epochs. Also, try different augmentations. Try maybe a different optimizer if you want. I use Atom with a fairly large learning rate, I've just realized. You can reduce that even more. And you can adjust your learning rate and plateau options here. And what you can do as well you can add more filters into VGG. Start at 32, 64, 128, 256. How about you start at 64, eliminating the 32 altogether, so it goes 64, 128, 256, and 512. And you can even add more dense layers here. May not be necessary, but try it. Play with your dropout values as well. You can even add a whole new convolutional layer here. So instead of stopping at 256, you can just go here and add one with 512. I'll do this for you, but you can do it on your own. Maybe change your activation functions, maybe change the initialization, although I wouldn't change, to be fair, I wouldn't change the batch normalization, activation, and HE normal, but you can if you want, but I wouldn't. I think those are the best for a VGG type model, like we're using here. And lastly, try for more epochs. Alright, a good value for this, a satisfactory value, would be 70%. So give it a go. Again, you can try different data augmentations as well. Give it a go and see how good of an accurate model you can get. Okay, so that's it for this lesson. What we're going to do next is run an age and gender detector, I guess you could call it that, or classifier, and combine them afterward into one super facial deep surveillance classifier. Okay, thank you. Hi, and welcome to chapter 18.3, where we're going to build a deep surveillance facial monitoring system that combines emotion, age, and gender recognition. So now let's go on into an IPython notebook in our virtual machine and start building this. Okay, so we're in chapter 18 on our notebook folders, but there's no 18.3 notebook file. Where is it? It is actually in here. Let me go back, I did that too quickly. Into the age gender estimation folder here. Alright, so click it, and what this is basically a GitHub project I pulled. It's one of the better ones, I should say, for age and gender detection. And the reason why I downloaded this in this code, and what we're going to do, we're going to use his pre-trained model, is mainly because this data set that it's trained on is not loaded here, I hope. Otherwise I would be taking up way too much space. Probably isn't. But this data set that he trained it on, is quite large. And I actually did have a project prior to this where we were training it on that data set for age and stop it, okay? For age and that's why. Okay, so in fact the data set is here. That is not good at all. Alright, so I'm going to delete that before I give it to you guys. Alright, back to this. Okay. So either way, when you're training this model, you actually can train on his model here. Alright, he has the code to train. However, it is not quick, and it is basically a standard training procedure, what we have done before, but it is not worth the effort to do on a CPU system. So I said, you know what, we will just use our pre-trained models, and we will his pre-trained model, and it's a good exercise too. Basically, executing someone else's model is actually, it may seem like cheating sometimes, but you can learn a lot, alright? So I'll quickly, this is his project here. Let's bring this up, alright? The first one we're going to do is basically, because he has some notebooks here, I should actually label what mine's are. So let's do that quickly, alright? So this is going to be 18.3, let's call this A. And the second one we're going to run right after, is where we combine them both. Because firstly what we're going to run is his age and gender detector, and this would be 18.3b. okay, so now let's bring this up. Let's take a look at this. Right, so this is what the link I wanted. This was his GitHub for his project. Okay, now I believe if I'm not mistaken, there was a slight issue with his project that didn't run off the bat, and I had to make some changes in the file. Luckily, I did make the changes in the file, so if you don't have to pull his code from scratch. His code is already in this folder that we saw here. So basically, what's good about this though is that he does give some instructions. If you wanted to actually train the model on your own, you can train it on different data sets as well. This is the data set he included in his file. You can train it here, or you can use some of his demo file. Is the file we're actually going to. That's the pre-trained weights. Let's open this and you can see it here. Okay, we don't want to download it because we already have downloaded it. and basically you can train it on the IMDb. Basically this IMDb dataset he talks about here, basically someone scraped IMDb's website, you know, Internet Movie Database website, extracted the faces and actually labeled the ages and gender, which might have been quite a tedious task, but they did it. Okay, so these are his results here for his pre-trained model. His loss is quite low for age and for gender, not that low in the end though, but it's fine. And so he probably stopped it, did some pre-trained early stopping and got the models out before accuracy and this stuff went to hell. Actually, I'm looking at the wrong accuracy. This is the one green and blue. Okay, so that's fine. Either way, definitely overfitting here. All right. Actually, that's not overfitting. That is actually on his training data set. So it's kind of weird results, to be fair. All right. Either way, it worked and fine. And as an exercise for you guys, if you're interested in seeing how this works, his code is here. It's fairly well documented as well, so you can take a look and try doing some cool stuff with this. What we're doing now is using his pre-trained model. So I basically extracted the code from his project code there, his demo code, and I'm doing it here in an IPython notebook. So let's step through this code quickly. It's not that different from the previous code, just some little things you should note. So firstly, this is how we load his model, and we have to specify a mod hash when we load his model. So go back to our face detector results. This is what gives us our faces, and this is what displays our results. Actually, let me just check something. I don't believe I'm using that function anymore, and I am right, I am not using it anymore. So let's delete it. Totally unnecessary. All right. So now these are the model parameters here. Okay. Just for now, you can leave these alone. Okay. Depth, K, weight, none. These are all the specifications for loading his model. Okay. His pre-trained weights. So we do that. So we have his model. We loaded it. We got the weights and everything from his model. It's an HDF5 format. So now set up the stuff. We get his model feedback. Sorry, these parameters now go into his model here, and model load. So we get his model now officially. All right. So we initialize our webcam here. Standard stuff. Standard stuff you've seen before. We get this. Now what I've done, I've made some changes to this code because the previous code I didn't tell you, but if a second person appeared in that diagram, it would only show one of you guys at a time. It doesn't show more than one face. It may even crash. I'm not even sure. You can do a test. Bring a friend. Okay, I have no friends with me right now. My wife is out, so I can't test that. But that's okay. So this is how I actually got it to work with multiple faces. So we do this here. Basically, we append the faces that we extract here, and then what we do, we use his model that we loaded here to make a prediction, and this prediction gives us two things: gender in the first array, male or female. I know there are many other genders right now, but for now it's just trained on male and female because those other genders will still look like male or female either way, so that's fine. All right. And so we have the predicted ages here as well, and these ages are in a bit of a funny shape here. So he does some reshaping, all right, and flattens it, and then we get the results here. So we get the predicted ages, and this is good. All right, so we get it now. Now what we're going to do, since we possibly have multiple faces in this file, is that we go through the faces and go through the results and display the results later on here. Okay, and that is it. This is what runs for our age and gender. So let's give it a try. It's loading. Probably loading his model. There we go. So that is pretty awesome. All right, what I'm going to do, I'm going to bring up a picture on my phone of a face, and let's try to simulate this with another person, or pretend person we're going to use. Okay, so it's actually harder than I thought. Okay. Yeah, okay. So my friend here, she has some good face pictures. I I hope she's okay with me using this. All right. Okay, so I'm going to bring this up here. Okay, so this is me. This is my friend. It is not detecting. Oh, there we go. Oh, it thinks she's a guy. I have no idea. She doesn't even find her face. And it still thinks she's a guy. Now, there's a problem here, and I hope you can see it. And I did actually see it in the code and didn't mention it to you guys because I was like wondering how it does not work the way it does. It's supposed to, doesn't it? And that's because, exactly as I said, it will detect the other faces here, but it only draws the results for one prediction here, because it's not appending to these results in any array. This is something I fix later on, by the way. So for now, though, just be aware that this age and gender detector only technically detects one face at a time, not two. And basically, this is something I also noted here. If you get this error, this is the error you'll see here, faces not being detected, it's because your webcam has not been turned on. So basically, if this happens, just go to devices and webcams and tick this off, okay? So that is that, and if for whatever reason this program crashes when you're messing with the code and the webcam isn't released, that will happen quite often, I'm sure. Just run this line separately to reclaim your webcam so that you can reinitialize it again later on. Okay, so now that was age and gender, 18A, 18.3A. Now let's do age and gender with emotions. That's the cool part. That's our deep surveillance part now. So again, let's load all of this. 10 seconds wasted of my life again. There we go. It seemed a little faster this time. Maybe it heard me complain. Okay, so now, this is testing emotion, age, and gender using our webcam. Now, I am not going to go through this code in super detail because it is a bit messy. However, what I'm going to tell you is that I have manipulated this code to support two faces, alright? So, let's give this a go. Bring up my friend's Instagram picture again. Okay, so we got an error. Color is not defined. Okay, I'm going to pause this and see what is happening here. Oh no, I know exactly what's happening. I was trying to do some color manipulation before. Okay, so BGR, split this, let's get back green. Okay, it is going to... Ah, damn it. What happened is that it claimed my webcam. It's not going to get an image. So what we can do, as I mentioned before, and I did not put it in this file in an accessible area, just put a cell below and reclaim my webcam. So I can run this finally again. 9 time today. There we go. So yeah, I'm not actually sad. I don't know why it thinks I'm sad. No, neutral. Let me bring up the multiple face. Oh good god, this is mirrored. This is confusing. Okay. Still not in. Why are you? Oh, there we go. Not in front of me. Alright. Come on, detector. Okay, for a brief second there it worked. Let me just bring this. This is much easier when you actually have a real person next to you. Okay, I'm gonna pause this and get a better picture. No offense, Nissa, but your picture is not being detected. Okay, so hold 1 second. Let me pause the recording. I'll not really pause it. I'll just fast forward this bit while I just waste time. Okay. Alright, so I found a picture of my wife I'm going to use from her Facebook profile. Maybe I should use like stock images. Seems like these images, I don't have the best luck, but we'll never know. Alright, so let's put it in front here. Alright, I just saw it detected. Come back, come back, come back in. This is actually harder than it looks because now I can't see my screen. And now it can't see my face and it's not detecting my face. This is... Alright, maybe I should just bring this back slightly. Ah, there we go. Okay, so I know my wife isn't going to be happy with this, but I think she's a guy who is 34 years old. Alright, that's probably because it's from a cell phone and the scale is definitely going to be off because of it. Thinks I'm 38 when I'm 34. Damn you, emotion. Sorry, age detector. Okay, I'm going to put this down. It's kind of annoying to hold. Alright, so what this means here is that this code works. It's not exactly 100% accurate with gender detection, as we can see, but that probably has to do with my little fake friends I'm using on my cell phone. These people are real, by the way. But either way, this should not happen that way, but it works. It works. It's good that it's detecting multiple pictures, multiple people. Alright, so this is good. Let's move on to the next one. Images. So let's run this. Okay, so now let's run this test on our images. Okay, yeah. Did not load anything in. My bad. My bad. Alright. Okay, so let's test this on some of our test images, and you can place those images in the images folder. I will show you here. Okay, so let's look at Donald Trump. Ah, this is quite funny. Thinks it's a female, 59. Looks much older in my opinion, but 59 and sad. That's me again. Added some extra years to me because I'm actually 34, but fair enough. Alright, Queen Elizabeth, and something funny is happening. It actually thinks this bouquet of roses is a guy who's 38 years old. Clearly, this is a bad example of it not working too well. Okay, but there's a reason for that, and I'll tell you afterward. Okay, Barack Obama, male, angry, 31, not the best. This is my wife, female, 30. She actually was 30 in this picture. This is quite good, and she was definitely happy here. All right, she was actually. This was the 2 days. Those pictures were 2 days apart, so apparently she aged a year in those 2 days. Okay, so that's cool. Now I said I'll tell you why, and that's because when we were doing this here, we were basically our Cascade classifiers don't crop enough of the face out, even with the default settings here, which I removed because you may have seen it in the code because I just cut and paste some of these images, the videos before, where I actually had some cropping being done, and I took it out because it was less accurate. But now, anyway, so dlib's facial recognition. Let's give this a try. Let's quickly run this. And I'll tell you about dlib. Well, it's running in the background here, but I'll tell you about dlib. What dlib is, it's a machine learning basically package that was built in C++, and now we can use it into Python, and it does a bunch of cool stuff. And what I'm using it here for is for face detection, but it actually can do facial landmark recognition. In my OpenCV course, in the parts I haven't included in this course, you actually do use the land point recognition on your faces for some cool projects, like yawn detection and face swaps as well, more advanced with face swaps. Alright, so, oh no, I'm sorry, I'm retarded. We are using dlib on images here. I really should label this better. I think in the last section we used dlib on the webcam. Yes. Okay. So again, okay, so it actually is worse now with Trump. He actually aged 2 years less. Fair enough. Me. Oh, okay, I'm younger here. 1 year younger. That's good. 54 female. Okay, fair enough. She's a lot older than that in this picture. That's fine. It got it generally correct. Barack Obama, 45. I think he was in his late 40s in this picture. Or maybe, this is very accurate actually, it's quite close. Again, my wife, she would not be happy with the age here, but it's fair enough. Again, because she was 30 in those pictures. Okay, but fair enough. So you can experiment with some different things. You know it's not going to be perfect yet. Age is actually a very hard thing to guess. I myself sometimes have thought someone was 30 in their 35 or 36, and I learned later they were like 50, which was embarrassing, but they were very happy about my mistake. So anyway, we can run this with dlib using the webcam. So I'm going to run this here, and I've changed my t-shirt, by the way, back to the one with the stain, unfortunately. Hope it doesn't pick up in this camera. No, it does not. And my bedroom doors are open here, it's fine. So again, this is quite cool. You can definitely see dlib has a slower frame rate here, okay? I literally did my hair thing like 5 seconds, 10 seconds before. Okay, so close that now. So the advantage of dlib though is that it is better at picking up faces. One thing you should have noted here is that it didn't mistake Queen Elizabeth's bouquet for a face like what our hard cascade classifier did. So you can generally see dlib is better and more robust. Remember before in hard cascade classifiers, it thought this was a face and thought it was a guy, which no, I would think it was a female either way, if it was a face, that is. But that's fine. So what I'm saying, the hard cascade classifiers are definitely faster. So if speed is your concern, or if your hardware, or if it's an embedded system, you can use hard cascade classifiers and maybe tweak some of the parameters, like the scaling parameters especially. This definitely helps, but these settings are generally well understood as the gold standard with hard cascade. Like this is the best depending on your application, but generally this is the best. So dlib may be more suited for some applications if its accuracy especially is of importance. Okay, so that's it for this chapter. I hope you enjoyed it, and I hope you build something cool out of this, and I hope you expand upon it too. Like you can actually take this code now and train over these models, or add in some new stuff as well. You can add in ethnicity as well. You can actually now take some of this data sets here, like this one, the first one, and maybe you can, if you can find like a labeled, like you can manually label the gender from this as well if you wanted to get even more accurate gender recognition. So this is pretty cool, and the challenge in bringing both of these together, which I probably failed to mention, is that they're both taking different size faces. They're both, one is taking in a color image, that's the age and gender, it's taking in a color image that's 64 by 64, whereas the other one, which is our emotion detector, is taking in a smaller and grayscale image. So you have to sort of do a little more processing here in our pipeline, and basically then you have to get the results and make sure they're lined up, like the same face is tied together with this age and gender and emotion, which is fairly easy anyway, and then plotting it correctly, and then making sure the labels follow the face around the image. So it was a fun piece of code to build, to be fair, but okay, so let's move on to image segmentation, and I'll talk a bit about medical imaging and UNet, which is a very cool CNN that does image segmentation. So this section is split up into 4 parts. Firstly, I discuss what is segmentation exactly, and I provide some examples of applications in medical imaging. Then I start talking about UNet and how it applies to image segmentation in CNNs. Then I define some units that we're going to need to know about, which is the intersection over union metric. And then we do our final project in the chapter, where we find the nuclei in divergent images. Hi, and welcome to chapter or section 19.1, where we talk about segmentation and its applications in medical imaging. So what exactly is image segmentation? So the goal of segmentation is to separate different parts of an image into sensible coherent parts. And what do I mean by that? Basically, you see this cat and this dog, and then there's a background definitely in the back. There's a bed or a couch, and then there are some curtains in the back. What we want, and a window actually, what we want is basically to do pixel level predictions. So we want to actually know exactly what pixels here belong to the dog, what belong to the cat, and what belong to the objects in the background. So as you can see, it's a pretty challenging task, because before what we were doing was basically a prediction of the entire image. And basically, if we fed this to a classifier, it would probably give a high probability of both cat and the dog being in the picture. But now what we want to do is actually segment the image now. So how do we go about doing this? And before I even explain that, let's talk about the 2 types of segmentation. So the first type is called semantic segmentation. And basically, this is just pixel level predictions based on defined classes. So we have example roads, persons, cars, and trees. So it's simple enough to understand, not simple to do, but we can pretty much see how it's done here. And you can imagine this has a lot of application in self-driving cars, because now you need to know what is a road, what is a building, what are like lamp poles, people, those sorts of things. So it's going to be quite useful for that application. Type 2. So now we're doing 2 different things here. We're doing pixel level predictions, which is exactly what we did before, but now we're actually doing object detection and actually object identification as well. So we can know person 1, car 1, person 2. So this is a more advanced level of segmentation. So let's talk a bit about the applications in medical imaging. So as you know, a lot of medical imaging necessitates finding and accurately labeling basically things they find in these scans. Because I don't know if you've seen a lot of these medical imaging scans. They are very, very hard to interpret, and I think you need some very skilled professionals analyzing and accurately assessing what they see in those pictures generated from the different scans. And basically often this task